welcome to the lecture video on part one of addition reactions of alkynes. Okay, so if you are using addition 1 or 2 of Klein, this will be chapter 10. And if you're using addition 3 and beyond, then this is chapter 9. So we're going to be talking about alkynes in this chapter. And so we want to remember some properties of the carbon-carbon triple bond. So recall that the triple bond is made up of one sigma bond, which is the head-to-head overlap of hybridized orbitals, specifically sp hybridized orbitals, and then the side-to-side overlap of p orbitals, which forms pi bond. So there are two sets of pi bonds that are orthogonal to each other and one sigma bond. And that leaves one other bond that carbon can make, for example, to another carbon or a hydrogen, again, using an sp hybridized orbital. So just like alkenes, alkynes have pi bonds that are reactive. And the pi bond can react the same way that it did with alkenes. So it can act as a base or a nucleophile. There's a lot of electron density that's weakly held between those two carbons, and that can be used to form sigma bonds. So we're going to be looking at addition reactions to alkynes, and you're going to notice that they're very similar to addition reactions to alkenes from the last chapter. Because there's two pi bonds instead of one, oftentimes the electrophiles that are added as reagents can add twice instead of once. So the reactions do have some differences, but you'll see a lot of similarities. Let's start off by talking about the simplest alkyne, and that is the common name for it is acetylene, and it's also known as ethyne. Acetylene is just two carbons that are triple bonded to each other, and each carbon is also bonded to one hydrogen. So it is used in blowtorches, and it's used as a precursor for the synthesis of more complex alkynes. And you'll see how we're able to add to the carbon chain, starting with what's known as a terminal alkyne, which is a carbon participating in a triple bond that's also bonded to a hydrogen. There are many different natural products that have been isolated that have alkynes in them. For example, estriano ecotoxin, which is found in the skin of frogs. So it's a toxic substance found in the skin, and native peoples would rub it on their spears and things like that, as to injure their prey more effectively. Okay, and then sometimes we even make synthetic alkynes. So for example, ethynyl estradiol is an active ingredient in many birth control pills, and it's synthetically made via the addition of a terminal alkyne to a ketone, which added this alkyne and formed an alcohol. So it's a synthetic hormone, like you might see its structure is very similar to like testosterone or other steroid-based hormones. Okay, so nomenclature. We want to talk, so this is the first time we're really going to be looking at reactions of alkynes and how to make alkynes in detail. And so since this is the first look at alkynes, we want to talk about how to name alkynes. So it's using the same procedure that we've been using to name alkanes, and then we learned how to name alkyl halides, alkenes. So it's the same procedure with minor modifications. So of course we want to first identify the parent chain, which should include the carbon-carbon triple bond in the case of an alkyne, because that alkyne is a functional group that has priority, and therefore we need to include that triple bond in the parent. We want to identify and name substituents just like we did before. Assign what's called a locant, which is a number to each substituent. So we'll number the parent chain, right? Being careful to give the carbon-carbon triple bond the lowest possible number, since it has priority over alkyl groups or halogens, things like that. And then we want to, of course, list the numbered substituents before the parent name in alphabetical order. Remember that the counting prefixes don't count towards alphabetical number, like di, tri, tetra, but other prefixes do count, like iso and cyclo. Also, sec and tert are considered counting prefixes, so remember that those don't count towards the alphabetical order. And then we need the locant for the first carbon in the triple bond, and it's either placed before the parent name or in between the root of the parent name and the "-ine" suffix. Okay, so we want to, again, identify the longest carbon chain, and it should include the carbon-carbon triple bond, right? So it's not just any old longest carbon chain, but the longest carbon chain including the triple bond. So for example, this would be, the parent would be heptine for this. So notice that important prefix YNE. Of course, name any substituents that you would find. And then we want to number the parent, number it in such a way to get the lowest number possible for the carbons that are participating in the triple bond, right? So we would want to number it this way so that we have a 2 before the "-ine, right? Instead of going the other way, which would have a 5 before the "-ine. So even though we get to another substituent going this way, remember that the alkyne takes priority over other substituents. So halogen groups, alkyl groups, those are considered to have no priority. And again, just like with alkenes, the locant is one number, not two, right? Of course, the triple bond bridges 2 carbons, but only the first number is necessary. The second number is assumed. And that number for where to find the alkyne, again, can come before the parent or in between the root and the suffix of the parent. Just like acetylene is a common name for the simplest alkyne, there are other ways to name alkynes that are considered common names. For example, the common method of naming alkynes is to use acetylene as the parent. And then any substituents, if they're simple substituents, can be named as substituents to the parent acetylene. So for example, methylacetylene, diisopropylacetylene, or notice the alphabetical order here, phenylpropylacetylene. Alkynes are also classified as terminal, meaning they're at the end of the chain. There's a hydrogen bonded here, or internal. And the reason for the classification is terminal alkynes, for example, can do some reactions that internal alkynes cannot do. Okay, so notice that we skipped chapters. We went into the chapter on alcohols. We're only going to be covering the nomenclature of alcohols. And the only reason for that is because alcohol nomenclature tends to pop up on the ACS exam that we're using as our final exam in this class. So even though most of the reactions of alcohols, or all of the reactions of alcohols, will be covered in the second semester of organic chemistry, we are going to just cover the nomenclature this semester. So again, alcohols are named using the same procedure as before, again with modifications. The parent chain in this case needs to include the carbon that the OH group is attached to. You still need to identify and name substituents. You want to give the carbon with the OH the lowest number possible. So as we've been covering these functional groups, we've been increasing in priority. So I've mentioned priority before, like I talked about the alkyne has priority over alkyl groups and things like that. So the OH group or alcohols have priority over alkynes and alkenes, right? Which have priority over alkanes and halogens and alkyl halides. So now, even if you have an alkene and an alcohol, or an alkyne and an alcohol takes priority over the alkene and the alkyne. So if we're naming it as an alcohol, because that's the highest priority functional group, then all other groups become substituents. And of course, we're going to list substituents before the parent in alphabetical order. And now the key suffix is "-ol", so it becomes like hexanol, heptanol, for example. And of course, we need a locant for where to find the OH group. And it can either come before the root of the parent. So for example, 2-heptanol, or it could come in between the root and the suffix, like heptan-2-ol. So again, we want to find the longest carbon chain that now includes the carbon that has the OH substituent, right? So for example, this would be hexanol, and then this would become a substituent on the parent hexanol. We want to assign a locant to the lowest possible number to the carbon bearing the hydroxyl group. So for example, starting from carbon 1 on the left, going to carbon 7, this is the correct way of numbering because we get the lowest number possible on the longest carbon chain for the OH group. This way would give lower numbers for the alkene, but remember that the alcohol has priority over alkenes and alkynes. And then we need to include that locant for the alcohol in the parent. So you have to place it before the root, pent, or after the root, or should be pentan, and before all. So 3-pentanol or pentan-3-ol. Okay, for cyclic alcohols, the OH group is always carbon number 1 because if you're naming it as an alcohol, then that's the highest priority functional group. So we'll start our locant numbering at that carbon. And then we want to go in the direction that will give us the lowest number possible for other substituents. So for example, we would have to start here, and then we want to go this way so that the methyls can come in carbon number 3, as opposed to going the other direction and have them at carbon number 4. And then don't forget, if there's chiral centers, that R and S, E, or alkenes could be E and Z. All of that stereochemical information needs to go in the name as well. Common names for some alcohols are also frequently used. For example, simple alcohols that have a simple R group and an alcohol can be named with the term alcohol as the parent. And then the simple alkyl group could be a substituent. So for example, isopropyl alcohol, tert-butyl alcohol. The IUPAC way for naming that would be 2-propanol or 2-methyl-2-propanol. And benzyl alcohol is also a common alcohol. And then just a brief mention of phenols. Remember, a phenol is when you have an OH group directly attached to a benzene ring, and the parent becomes phenol. We will start counting at this carbon and then go in the direction that gives the lowest number possible for any other substituents. So for example, this would become a 4-chloro-2-nitrophenol. All right, back to alkynes. You may recall from chapter 3, when we talked about acidity, that terminal alkynes have a relatively low pKa, meaning they're more acidic than other hydrocarbons. So for example, one of our least acidic hydrogens is a hydrogen attached to an sp3 hybridized carbon, like that of ethane. If you have a hydrogen attached to an sp2 hybridized carbon, the pKa goes down a little bit. But if you have a hydrogen attached to an sp hybridized carbon, it goes down substantially, right? This is almost 20 pKa units, which is a huge difference in pKa. So the acetylene or any terminal alkyne, because this could be hydrogen or a carbon, those can be deprotonated if you use a strong enough base, right? Remember that pKa of 25, while it's relatively acidic for a hydrocarbon, it's not super acidic. So it's going to need a pretty strong base to deprotonate it. But assuming you have a strong base, you would be able to deprotonate either acetylene or a terminal alkyne to get what's known as an acetylide ion or an alkanide ion. This was just an R group, which generates a nucleophilic carbon. Nucleophilic carbons are pretty hard to come by. Oftentimes, carbon is bonded to more electronegative groups like halogens or oxygen, and as a result, it has a partial positive charge commonly. It is not that easy to get carbon with a partial negative charge or a full negative charge in this case. So this is really something important to realize, that you can get a carbanion if you start with a terminal alkyne and treat it with a strong enough base. And if you recall from chapter 3, we use ARIO and specifically the orbital to explain why acetylene is a stronger acid than ethylene, which is also in turn stronger than ethane. So the reason for that has to do with the orbital in which the lone pair and negative charge reside after deprotonation of those compounds that are being used as an acid. So for example, this is the conjugate base of ethane. This would be the conjugate base of ethene. This would be the conjugate base of ethyne, also known as acetylene. And notice that when you deprotonate, you get a lone pair that is in a different type of hybridized orbital, specifically sp3, sp2, and an sp hybridized orbital. And remember that the sp hybridized orbital has 50% s character. As a result, it's more spherical, and the electrons are held closer to the nucleus of the carbon and are therefore more stable. So the more stable the conjugate base, the more acidic the acid will be. Okay, so we talked about if you use a strong enough base, you can deprotonate acetylene or a terminal alkyne. A terminal alkyne would just be, this part of the molecule is the same, and this would just be an R group like methyl or propyl, etc. So recall that terminal alkynes have a hydrogen attached to a carbon. This one has two, but at least one hydrogen attached to a carbon that has a pKa of about 25. So if you use a strong enough base, it can definitely deprotonate it. So if we compare, for example, this is considered called sodium amide and sodium hydroxide. You compare the ability of these two bases to deprotonate a terminal alkyne. You can either compare pKa's if available, or use ARIO, but remember that this is technically an exception to ARIO. So it's better to use pKa's. So we're looking for the weaker acid. The equilibrium will always favor the weaker acid or the more stable base. And so only this base is actually strong enough to deprotonate the terminal alkyne, in this case acetylene, to form the, in this case, called acetylide ion. Sodium hydroxide is actually much weaker than sodium amide, and the equilibrium lies to the left here, so it is not strong enough to deprotonate acetylene or terminal alkynes. So again, this is a terminal alkyne. It's just like acetylene, except for on one side there's a carbon-based group instead of a hydrogen. This is any terminal alkyne. If you use a strong enough base, you could definitely get an alkanine ion, which contains a nucleophilic carbon, which can be used with electrophiles to perform reactions. And we're going to talk about that a little bit later in the chapter. So the strong base that's most common is sodium amide, but definitely other strong bases could be used as well to deprotonate that terminal alkyne. So remember that base strength and acid strength are inversely correlated or inversely related. So up here with the weakest acid, the conjugate base of that would be the strongest base. So we just need any base whose conjugate acid is a weaker acid than the terminal alkyne, which has a pKa of about 25. So if the pKa is higher than 25 of an acid, the conjugate base will be strong enough to deprotonate it to form the alkanide ion. So these bases will deprotonate a terminal alkyne. This is like butyl lithium, for example, would be a common way to get a butyl group where the carbon is an anion. Sodium amide, sodium hydride, those are all strong enough bases. For example, alkoxide or hydroxide bases are not strong enough. Okay, so before we talk about reactions of alkynes, we actually want to start off with how do we synthesize an alkyne? How do we prepare an alkyne? So just like alkenes, alkynes can be prepared by elimination reactions. When we were looking at forming an alkene, we started with an alkyl halide, treated it with a strong base to do an E2 reaction, and we got the alkene product. If we want an alkyne, now we need 2 pi bonds, so we need to do successive or 2 elimination reactions. With 2 elimination reactions, that means we need 2 leaving groups and 2 hydrogens at the beta carbon to do 2 successive E2 eliminations in order to synthesize an alkyne. So for example, if you use a strong base, it can do the first elimination to form an alkene, and then because you still have a leaving group and you still have a hydrogen beta to that leaving group, you can actually add a second equivalent of base and go all the way to an alkyne. So this is an example of what's called a geminal dihalide. That's when the halides are attached to the same carbon. And then we also could use a vicinal dihalide where the carbons are attached to adjacent carbons. I always think of this one as being in the vicinity, right, but not exactly attached to the same carbon. So what are the reagents used to do that double elimination reaction to get the alkyne? Well, what we would actually do is take either a vicinal dihalide that is shown here or a geminal, this is a geminal dihalide, or you could take a vicinal dihalide, and you can treat it with actually 3 equivalents of sodium amide, which is typically prepared in ammonia by treating it with sodium metal. We have this solution of at least 3 equivalents of sodium amide in ammonia. What do those 3 equivalents do? Well, the first 2 do a normal E2 reaction twice to get the 2 pi bonds to form the alkyne. The third equivalent is actually used as a base to deprotonate the terminal alkyne, because as soon as we have the 2 pi bonds, now this hydrogen is fairly acidic, pKa of 25. So this is a strong enough base to deprotonate it. And this is used as the driving force, or the step that essentially pushes the reactions toward the product, shifts the equilibriums towards the elimination product. Once we get the alkanide ion in solution, just need to do an aqueous workup to isolate the terminal alkyne. Even just adding water is a strong enough acid to deprotonate a terminal alkanide ion to form a terminal alkyne and sodium hydroxide. So recall that the equilibrium when we were trying to deprotonate the terminal alkyne favored the reactants. So then the reverse reaction is actually favorable. Remember, sodium hydroxide is not a strong enough base to deprotonate a terminal alkyne to form the alkanide ion in water, which means if you take an alkanide ion in water, it will be favorable to form the terminal alkyne in sodium hydroxide. So again, that third equivalent is needed to initially deprotonate this to drive it to an alkanide ion, which we could then just reform the neutral alkyne protonated version, right, with just adding water at the end of the reaction. So this is what that would look like. Here is a geminal dihalide. Here is, it says excess, which basically in this case means at least 3 equivalents of sodium amide in liquid ammonia, followed by that aqueous workup. We'll do a double elimination, deprotonation, followed by reprotonation with water, and will give us our terminal alkyne. So now that we know how to prepare alkynes, we're going to transition to what can we do with an alkyne? What reactions can we do to form a different product, to convert it to something else? So the first reaction we're going to talk about is catalytic hydrogenation. So remember, with alkenes, if we treat an alkene in the presence of hydrogen gas in a metal catalyst, such as commonly platinum, nickel, or palladium on carbon, we can get reduction of the 2 pi bonds and addition of additional hydrogens, right, across those 2 carbons. So essentially reduction of the triple bond all the way down to a single bond. And this occurs in quantitative yield. So just like an alkene, alkynes can be reduced. It just reduces both pi bonds instead of only 1 pi bond. The first addition of hydrogen gas does produce a cis alkene, suggesting that just like we talked about in the previous chapter when we went over hydrogenation, and we said it's a syn addition, it's the stereoselectivity of the reaction is syn addition. This is still further evidence that syn addition is what is occurring. Because if you were to trap and isolate a small amount of the intermediate, you would notice that this cis alkene is being formed before the next hydrogenation converts it all the way down to an alkene. What if we actually wanted to stop at the cis alkene, right? That would be advantageous. We may not always want to reduce the triple bond all the way down to a single bond. What if we wanted to stop at the alkene stage? Specifically in this case, to synthesize a cis alkene. Well, we could use hydrogen gas, but we would not want to use a normal platinum, nickel, or palladium on carbon catalyst. Instead, we would want to use what's called a poisoned catalyst. A poisoned catalyst is a catalyst that will catalyze the first reduction of the pi bond, but not the second reduction of the second pi bond. And so essentially it catalyzes the first reduction, but not the second reduction. So common poison catalysts are Lindlar's catalyst or a nickel boron complex. So Lindlar's catalyst contains palladium as its base metal, but it's poisoned with quinoline, which coordinates to the palladium, and barium sulfate as well. And methanol is just the solvent that this is prepared in. So what's happening here is the poison catalyst will catalyze the first reduction, right, or the first addition of hydrogen gas across the first pi bond, but not the second step. And so we're able to stop at the cis alkene, which could be really synthetically advantageous if you want to form a cis alkene. What if we wanted the trans alkene, right? What reaction conditions would produce a trans alkene? Well, if we want the trans alkene, we need to do a dissolving metal reduction. The reagents are sodium metal and liquid ammonia, and it will reduce an alkyne down to a trans alkene. This reaction is stereoselective for anti-addition of the 2 hydrogens, thus giving us the trans alkene because the 2 hydrogens get added on opposite sides of the pi bond. So here's the entire proposed mechanism of the dissolving metal reduction. But we're actually going to look at each one of these steps individually. Let's consider the first step of the mechanism. The first step is, remember, we're adding sodium metal in liquid ammonia. So sodium metal definitely wants to give up electrons to become sodium plus, where it's much more stable. So it can give up its electron in a single electron transfer process. And because we're transferring single electrons, recall that we need to use fishhook arrows instead of our double-sided or double-barbed arrows. These fishhook arrows show single electron movement as opposed to movement of pairs of electrons. So the sodium metal will donate an electron. One of the pi bonds breaks up to form a radical anion. Oh, I don't know why that says radical cation. I did not notice that until now. Sorry, you should change this, and I'll change it after. So it doesn't say that in the slides that you get, but this should be a radical anion intermediate. From there, well, the radical anion will form specifically in this orientation where the anion and the radical are on opposite sides of the pi bond. And that's because there's a steric repulsion when we place them on the same side of the pi bond. So it's lower energy to place them on opposite sides of the pi bond, so they adopt this sort of anti-geometry. From here, this is very, very basic, and even ammonia, which is a weak acid, can protonate it. So ammonia can provide protons to protonate this and form NH2- as a byproduct. Sodium metal gets involved again and does another single electron transfer process to convert this radical into an anion that can then get protonated using ammonia. And notice because of the preferred geometry of the radical anion intermediate, we end up adding both hydrogens to opposite sides of the pi bond, leading to our transalkene product. So let's look at a summary of reduction reactions. So we know that we can reduce pi bonds and reduce functional groups, right? So we can go from an alkyne to an alkene or reduce it all the way down to an alkane. So typical hydrogenation with hydrogen gas and metal catalyst will reduce the triple bond all the way down to a single bond. Or you could stop at an alkene through using a poison catalyst. So over the arrow, it's often written as H2 with Lindlar's catalyst. Or if you wanted the transalkene, you could do the dissolving metal reduction reaction with sodium metal and liquid ammonia. Either type of alkene could be hydrogenated to an alkane under typical hydrogenation conditions with hydrogen gas and a metal catalyst. Okay, skipping ahead to the end of the chapter for now, I want to cover the alkylation of terminal alkynes because this comes up in your first activity. So recall that terminal alkynes can be deprotonated if you use a strong enough base, such as sodium amide. So NH2- can be protonated and form an alkanite ion. Remember that we talked about the fact that this carbon is now electron rich and therefore can act as a nucleophile potentially, and it can react with electrophiles, such as alkyl halides. So essentially what this is doing is it's acting as a nucleophile in an SN2 reaction. This is considered a strong nucleophile, and we can actually do SN2 reactions, and this will form a new carbon-carbon bond. Right? This is really important because this is the first reaction we are really learning to form a new carbon-carbon bond. So if you want to go from a substrate that has 4 carbons and you need it to react to have 6 carbons, then you need a way to make a new carbon-carbon bond. So starting now and until the end of the organic chemistry sequence, we will really highlight and make a big deal out of reactions that form new carbon-carbon bonds. Because there are, you start off with very few options and then get more, right? But there are great ways to increase complexity in organic molecules. Right? We often need to form new carbon-carbon bonds. So highlighting reactions that do that are a fantastic way to remember how to do it synthetically if you need to do it. So let's look at an example, right? We need to take a terminal alkyne because it has to be one with an acidic hydrogen. If you treat this with one equivalent of the strong base, sodium amide, it will become deprotonated to form an alkanide ion. And then if you treat that with an unhindered alkyl halide, such as a methyl, or in this case, primary alkyl halide, you will, it will undergo an SN2 reaction and form that new carbon-carbon bond that we're talking about. Unfortunately, this only works with methyl and primary halides. If you use a secondary or tertiary halide instead of a methyl or primary halide in step number 2, then, then E2 elimination will dominate over SN2 substitution. So unfortunately, substitution would not occur and we would not get a new carbon-carbon bond. So we just want to remember that the alkyl halide must be unhindered. It has to be methyl or primary such that it undergoes a very facile SN2 substitution reaction. If you start with acetylene, you can undergo 2 successive alkylations. You can treat it with sodium amide followed by the first alkyl halide to form the first carbon-carbon bond. And then we can do that process again to form a second carbon-carbon bond. Now, these 2 R groups could be the same or they could be different. You don't have to use the same one. You could first start with adding a methyl on one side and then an ethyl on the other side, for example. You just need to do those one at a time. And even if you're adding the same group, you still have to do it one at a time. So here's a double alkylation of acetylene. It must be stepwise. You can see first they added an ethyl with ethyl iodide, then they added a methyl with methyl iodide. Both of those are unhindered alkyl halides, either methyl or primary. So great substrates for this reaction. And we've gone from something that only has 2 carbons to now something that has 5 carbons. So complex target molecules can be made by building up carbon skeletons and then converting functional groups to new functional groups. So once we've built up the carbon skeleton, now we could convert this alkyne via other addition reactions to new functional groups. And a lot of those addition reactions will be covered next time.